Can you hear me? Hello?
Yeah.
Okay, sorry. I've had some troubles for the last 5 minutes with the network. I hope it doesn't go down again. Okay, so can you hear? Can you see the slides now?
Yes.
I hope so.
Yes.
Very good. Thank you very much. Sorry. So thanks everyone for coming. So this talk again is not going to be about dark field X-ray microscopy per se, but rather diffraction contrast tomography. So why would we actually want to do that? Well, probably this is known by everyone here, but DCT can actually be used to scan larger regions of samples and actually quite a few grains in just a few minutes. And that can be actually a very good way for locating features that we want to inspect later with dark field X-ray microscopy. For instance, here I have an example, which is polycrystal. And we can actually see immediately that, for instance, the grain misorientation, or let's say local misorientation, sorry, is higher either in certain grains or in certain regions. So if we wanted to study that, we could just use DCT to basically locate the most interesting regions and go ahead with the finer analysis later. So probably everyone here knows DCT, but just to give a quick recap. So it's a non-destructive characterization technique for the 3D brain microstructure. It allows to both acquire the transmitted beam and the diffracted beam. It takes thousands of images over 360 degrees, and it uses hard X-ray box beam illumination. So the figure I have here for the acquisition times is pretty outdated. So with the EBS now, we're down to 5 minutes, and we can acquire information about 1,000 grains with that. So that's pretty interesting, I would say. But traditionally, it has assumed undeformed grains or undeformed materials to start with, which is in contradiction with what I just said before, because we might want to be looking at deformed features. So some time ago already, we started to expand this model and go away from the undeformed materials underlying model. So we, if we think about it, if we want to model the formation or even just crystal misorientation, that would add 3 unknowns for each space location, so for each voxel or unit volume. And that means that if we use this representation, so for an average local crystal orientation, the projection geometry, as we can see here in the image below, it gets complicated, okay? So there are approaches that work with this, for instance, the one of Bob Suter from the US. But for our type of illumination, it might not be suitable. So we came up with something different in the end. Actually, I should say that, yes, since now in that case, so for the 3D vector space representation, which was the one that I just mentioned, the projection geometry actually depends on the current solution. So this means, and we will see this in a second, this means that we have a nonlinear problem, okay? So if we instead just expand, okay, there's three unknowns into a 3-dimensional space, we get a scalar 6D space representation. And in this case, we have an associated volume for each real space volume for each sampled orientation in the 3D orientation space. And for those volumes, the geometry is fixed, okay? So this simplifies everything, because at that point, we can project each volume with standard tomography codes, okay? So this just is to show that with 3 different orientations, we have the fixed projection geometry for the 3 of them, and it's from the very start to the very end of the iteration process for the reconstruction of the local misorientation. So how do we do that in the end? This is a tomography problem, and tomography problems are usually linear systems. Okay, they can be represented as linear systems of equations, and where W in this slide up in the bottom, in the top, sorry, is the projection matrix or the projection geometry essentially. X is the unknown, and in our case, it would be the 6-dimensional space. And Y are the images. So in our case, the diffraction images. So normally to deal with indeterminacy and noise, this is cast into a minimization problem. And as I said, I want to remind here, if we wanted to go for the vector 3D field, this would be a nonlinear problem because W would depend on X. But again, we linearized it by unfolding it, and the problem is that this creates lots of unknowns. Actually, many more. We're subject to the curse of dimensionality, actually. So what we can do for dealing with that is to introduce some priors, and by that I mean we can already assume that all the reconstructed intensities will not be negative because that would be absorption. And also we could think of grains that are homogeneous in real space, so that their concentrations doesn't change throughout the grains and so on. And this can lead to priors, okay, about the reconstruction. And this can help a lot in stabilizing the reconstruction and actually making it converge to something that is physically feasible. And once we have this, basically we have everything for reconstructing, and we can reconstruct. So this is a quick example. So in this case, we had a slightly deformed material. So it was very little, actually, the local misorientation that we had in the grains. But actually, we see here that there were gaps into this grain map because we couldn't index some of the grains throughout the process because due to overlap and being neighboring grains and so on. So what we said was, can we actually bring the reconstruction algorithm to another level and say just pick an arbitrary bounding box in orientation space, take the associated diffraction images for that, and just reconstruct blindly. And it turned out that this approach could allow us to index grains, okay? So this allowed us to create space filling maps, and with some other trickery, we could refine the space maps even better. So, however, this is a nice result, but it's not always that easy, right? So in this case, we have another example where we had some smooth gradients inside of the grains, and again, misorientation gradients. And we had twins. I believe they were deformation twins in this case. But basically, we saw this lamellae forming across the grains. But our reconstruction, it could actually reconstruct them. So we modified the algorithm to take into account multiple bounding boxes in orientation space, which was basically reconstructing on a disjoint 6-dimensional space, non-connected, so to say. And it could work, but we see, unfortunately, that the resolution wasn't the best. So we could see these grains, but it was not ideal. And also, in this data set, we noticed the presence of slip bands. We could see that from the diffraction images and also from the EBSD. But there was no sign of that in the reconstruction. So probably the resolution was not good enough. More recently, I was just sent this by Wolfgang yesterday. More recently, actually, we have seen some orientation contrast due to what looks like slip bands. But again, having better resolution, spatial resolution, would not damage us at all. And here, actually, Topo-tomography enters the chat finally. Topo-tomography is a close sibling to DCT, but also to dark field X-ray microscopy. And we're basically realign one grain plane normal with the rotation axis of the sample stage. and we bring that into diffraction condition. And as we rotate around the 360 degrees, basically the diffraction spots for that plane normal stays more or less in the same position on the detector. So what changes with respect to the CT is that we can basically zoom in with higher resolution detectors, essentially, or higher magnification, what that means, and have like better resolution for our images. So can we actually integrate this in the framework that I just explained? Yes, we can. So we developed a generalization of the projection, forward projection and back projection models for the 6D DCT, and that applies. I have the equations here. They might be looking a bit cryptic, but the I term is the thing that actually depends on the geometry. Everything else is the same. And we can indeed reconstruct orientation resolved Topo-tomography volumes, okay? And we can actually join reconstructions from DCT and Topo-tomography data. Why not? Or take, at this point, DCT scans with different spatial resolutions, different propagation distances, blah, 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 and still get reconstructions. So as we haven't applied this to real data yet, we did extensive simulation. And here I'm going to show basically these results on the simulation. Here we have a simple square grain where basically we have obviously some misorientation inside. I forgot what I think it was 1 degree misorientation total. And we can see that we have some local crystals, say sub-grains inside of this grain. And if we think of, by the way, Topo-tomography cannot resolve the misorientation along the axis of rotation, obviously. We would have to sample another plane normal for getting the information for that. And this is reflected in the reconstruction error here in the bottom row, where for the third dimension, basically we have complete insensitivity with Topo-tomo. But if we join DCT and Topo-tomo, so in this case, we had a DCT scan with 2.5 micron pixel size and a Topo-tomography scan with pixel size of 2.75 microns. And we can see that if we try to super resolve the DCT scan at the 0.75 micron resolution, it is blurred, essentially. So this is the middle column. But if we plug in also the Topo-tomography information, let's say the Topo-tomography images, at that point, the reconstruction gets much, much better, especially close to the edges of the, so at the grain boundaries where we have the most deformation. So, as I said, this can be expanded to be using also higher resolution DCT, and this is the case for the third row. And here we can see that basically the error both in the locally reconstructed intensities and the misorientation, they basically go down as we plug in higher resolution, higher quality information. So this brings me, oh, yeah, it doesn't work. I'll switch quickly to some video because there is hope that we can actually see. I hope you can see this video actually. There is hope that we can see this lip bands because we can see this contrast, this orientation contrast in the Topo-tomo images. This is a Topo-tomography image, obviously, scan. And so we hope that by having this higher resolution, we can finally resolve those features in our joint DCT and Topo-tomography reconstructions. So as I want to close this presentation, as I said, I just want to remind you that DCT, thanks to its very quick acquisition times for a large number of grains, it can be basically a pre-characterization step for dark field X-ray microscopy for identifying basically the interesting features. and that by plugging in together information from topo-tomography, we hope to get higher and higher accuracy and resolution for the subgrain disorientation reconstruction. So thank you for your attention, and that's it.
Yeah. Thank you, Nicola. I can't see questions in the Q&A. So there is Hugh Salmons has a question, raising the hand at least.
Thanks for the really interesting talk. How feasible is it in your mind to make a 3D reconstruction of dark field microscopy data taken in this topo-tomography configuration?
It boils down to having this forwards and back projector figured out, essentially. At least to my understanding, I might be wrong. But sorry?
Sorry, keep going.
What did you say?
Yeah, I said keep talking, sorry.
Sorry, my bad. So if we can identify this forwards and back projection model, I know that it's rather simplified maybe in, or at least the relationship between the different pixels and the images in dark field X-ray microscopy. The relationship between them and the final volume is rather simplified because you have this lens in the middle that basically sorts out lots of things. And in principle, I don't see anything blocking building such a reconstruction scheme, let's say. It really boils down to the projectors, in my opinion.
We should try to fix that.
I'm up for that. I'm down. Let's do it.
Good. We'll take you up on that offer.
Sorry?
We'll take you up on that offer. I think we already have some data.
Okay, very good.
Okay. No further questions? You're right in time for a short one. I had one